Dear colleagues, in this presentation I'd like to share some of our results on the effect of sulfide dissolving pulp properties on the performance in viscose production during a pilot scale experience. This work was done in collaboration with Kaima pulp mill, but also with the Center for Nanotechnology and Smart Materials. Unfortunately, due to the technical problems, I cannot record the image during this presentation, so I put my picture instead. Sorry for this inconvenience. The global viscose fiber production grew at an average rate of nearly 8% last decade. As you can see from this figure, the production of viscose almost triplicated last 2 decades worldwide. This steady trend is driven by an increase of the world's population and needs for the textile industry, while the cotton production is no longer efficient to meet the market demands. The most common raw material for the production of viscose is a dissolving pulp with some specific characteristic arising from acid sulfide or pre-hydrolysis craft processes, which contribute almost to equal amounts. More than 95% of dissolving pulp is processed to iron by a conventional viscose method, and less than 5% is produced by direct dissolution in ionic liquid, for example, in such process as lyocell. The major quality parameters of dissolving pulp are related primarily to their purity, to the high content of cellulose, low content of pentazone, lignin, and extractives, but also to the restricted intrinsic viscosity. Another quality parameters related to the processability of the dissolving part to viscose and are characterized by reactivity and the filterability. The reactivity refers to the ability of the dissolving pulp in reaction with carbon disulfide under predetermined alkaline condition. The higher the reactivity, the easier is pulp to shuntate and to dissolve in the alkaline solution. The filterability, the Chinese variant at least, indicates the ability of the dope to filtrate under specific conditions, just showing the extraction facility via spinnerets. The higher filterability, the better filterability, the shorter is the time necessary to filtrate the certain volume of the dope. The dissolving pulp processability to viscose varies significantly depending on the origin and the process history of the pulp, such as these parameters determine the difference in cellulose physical structure. So it's extremely important to define the optimal parameters for each particular pulp in order to obtain the best economical and technical results for the viscose production. Otherwise, the condition, of course, can be adjusted, but this leads normally to the losses in the viscose yield, worse productivity, excessive consumption reagent, and decreased quality of final fibers. This information is not available for the eucalyptus sulfide dissolving pulp. And was the major target in our study. Accordingly, the dissolving pulp obtained from eucalyptus acidic sulfide pulping process was subjected to production of viscose on the pilot scale, and the quality characteristic of the pulp were related to the basic quality parameters of the viscose fiber. In addition, the dissolving sulfide pulp was used in the pilot trial of the iron production by alternative iron cell F process using ionic liquid. For industrial dissolving sulfide pulp were involved in this pilot trial. All pulp was TCF bleached to 91% of azole. The basic difference between the pulp was the intrinsic viscosities that grow from pulp A to pulp D, different contents of the pentazone, also different reactivity from 50 to 60, and the filterability from nearly 10 to 160. The other parameters of the pulp were quite similar for all of them and did not affect the processability of dissolving pulps. In the pilot trial, the dissolving pulp is first mercerized in the stripping and pre-aging process, being further reacted with carbon disulfide to produce cellulose xanthate, then further dissolved in diluted alkali, and after ripening are subjected to the precipitation in the pulping equipment. The extruded fibers are first coagulated in the coagulation bath, being spun further using a series of roll and gutted, washed, and cut into the staple fibers after this being opened and conditioned before the analysis. All obtained fibers were analyzed by FTIR and X-ray diffraction for their structural parameters like crystallinity, orientation index, average crystalline weight, and the specific area was determined by sorption isotherm by bed area. Tensile properties were determined according to standard procedure. Alternatively, the iron fibers were prepared from dissolving pulp also by ion cell F process. In this case, the pulp in the form of fluff pulp was dissolved directly in the ionic liquid, and the prepared dope was then further filtrated and the molten dope subjected to extraction. The extruded fibers were coagulated in the water bath at 10 degrees, and after the spinning was prepared the staple fibers, which were opened, washed, and the final fibers were analyzed. I have prepared a short film to demonstrate how it works. Also, the viscose dope for all pulps was prepared by the same manner. Its behavior anti-extrusion and coagulation differs substantially. As we can see, for the pulp A, B, the uniformity of extraction was pretty good. It was a little bit worse for the pulp C, and in the case of pulp D, we observed periodical clotting of the spinnerets. The same for the coagulation behavior, that was pretty good for the pulp E and B. For the pulp C, we had some problems, and the coagulation behavior of the pulp D was the worst. We can see also this is reflected by the color of obtained fibers. Regarding the spinability, I can tell that for the A and B pulp, we practically have similar spinability, which was much worse for the pulp C and especially for the pulp D, when the periodical breaking of the fibers have been observed. Of course, the peculiarities in the extrusion and coagulation of fibers reflect their shape. As we can see at the left figure, the fiber obtained from pulp A and B shows good homogeneity and perfect surface. In the case of pulp C, we can see the fibers with irregular surface, but also some hollow fibers and folded fibers that we can observe especially well in the right figures. The surface of fiber from D pulp was irregular and contained debris and external splitting. This is probably a result of the inhomogeneous sedimentation of the cellulose, but also due to its poor reactivity and filterability. Regarding the strength properties, we can see that from pulp A to pulp D, the tenacity practically increased constantly. So, with the increase of intrinsic viscosity of the pulp, the strength properties were increased also. The elongation also would decrease from pulp A to pulp C and drop down for the pulp D, probably due to the worst spinability of this pulp. In general terms, we can tell that pulp with intrinsic viscosity below 450 cubic centimeters per gram is highly prejudicial for the strength of the viscose fiber. At the same time, pulp with intrinsic viscosity higher than 550 is hard to process into viscose. In the right image, we can see two pulps obtained by different processes, by conventional viscose fiber and by ion cell process. In this case, the tenacity of the viscose fiber was 3 times less than the tenacity of the ion cell fibers. And ion cell fiber have the half of the elongation as the viscose fiber. This is because of less degradation of cellulose during ion cell process than during the conventional viscose process. The physical properties of the obtained fibers were assessed by FTIR and X-ray diffraction. The summary of the results we can see on the table at the right. In this case, we can see that the crystallinity of the fibers increased gradually from the pulp A to pulp D, so accordingly to the intrinsic viscosity of the initial dissolving pulp. The same for the diameter of the crystallines. It's also important to note that orientation factor was decreased along from pulp E to pulp D because of the less spinability of this pulp. So, finalizing these results, we can assume that fiber strain corroborated with the cellulose crystallinity and the lateral crystalline dimensions. These figures show some relations between the intrinsic viscosity of dissolving pulp and the reactivity, filterability, and tenacity. As we can see in the right figures, the tenacity practically almost linearly increases with the intrinsic viscosity of the pulp, but however, at certain point at 550, the filterability is also increased even exponentially. In this case, the processability of this pulp is difficult. So it seems that filterability between the something like 10 and 60 seconds are the optimum. Regarding the pentazone content, we can tell that the quantity increases with the intrinsic viscosity of the pulp, that it's understandable because of the less degradation of pentazone during the pulping and bleaching process. The reactivity is not so evident in our case. It's grow up from 450 to 500 and then decreases. The problem is that reactivity depends on the impurities, but also physical structure of the pulp. When the pentazone content is too high, this difficult the reactivity of the pulp. But when xylene content is too low, due to the ornification of the cellulosic fibers, the reactivity also decreases. It seems that the best reactivity was achieved with the pulp viscosity between 450 and 550 centimeters cubic per gram. As the brief conclusion, it can be noted that the acceptable range of pulp intrinsic viscosity to produce viscose between 450 and 550 correlated with the filterability of about 10 to 60 seconds and the reactivity as high as 60%. The residual pentazones below 3% and alpha cellulose content as high as 92% could be considered as the target values. The tenacity of the fibers depends strongly on the physical structure of regenerated fibers and has increased with the increase of the degree of crystallinity of regenerated cellulose and the lateral dimension of crystalline weight, rather than from orientation of cellulose fibers. The comparison between the ions cell and viscose fibers revealed almost 3 times strength of the former, albeit with the half of maximum elongation. Being the more versatile and ecologically friendly Einstein F process represent an excellent alternative to conventional viscose method for the production of rayon fibers from eucalyptus dissolving pulp. I'd like also thanks Siseko and Keimer for the financial support of this work, also Professor Herbert Sixter for his supervision of the pilot trial, but also all master students and PhD students involved in this pilot trial.
Thank you very much to everybody for attending to this presentation. My name is Victoria Rigual. I am postdoctoral researcher at the Complutense University of Madrid in Spain, and I'm going to present the work entitled Hydrogels from Physical Ion Gels formed using eucalyptus and olive pulps as raw materials, a rheological study. This work has been developed in collaboration with the Instituto Nacional de Investigación y Tecnología Agraria y Alimentaria from Spain, in the frame of the projects Lignocellusolve and Sustec. The proposed work aimed to formulate gels, concretely from eucalyptus and olive bleached pulps. These two pulps have one main difference with other works, that is the use of pulps instead of cellulose. That is an industrial stream. Furthermore, eucalyptus and olive pulps are also different among themselves. Eucalyptus lignin, xylan as part of hemicellulose, and ashes are considerably lower than in olive pulps. The increasing awareness towards green chemistry has arisen the focus on the employment of bio-based materials. Around the possible materials to be formulated, gels have been emerged as interesting biomaterial. Gels are defined as two-component colloidal dispersion with a continuous structure with microscopic dimension that is permanent on the time scale and is solid in its rheological behavior. In this work, we are going to focus on two types of gels. Ionogels are hybrid materials where the liquid phase is an ionic liquid immobilized in a three-dimensional network presenting a solid-like behavior. The nature of the interactions between the ionic liquid and the solid can be either physical or chemical, with covalent bonds. Shifting the ionic liquid by water may lead to the formation of hydrogels directly from ionogels that are defined as 3D polymer networks that can absorb large amounts of water through cross-linking with chemical or physical bonding. A remarkable characteristic of this kind of gels is their biocompatibility, which makes them appropriate in tissue engineering, biomedicine, or 3D bioprinting areas. In order to determine the mechanical structure or nature of materials, the determination of the rheological properties is essential. Through rheology, we can study the formation of macromolecular structures, gels, to understand the micromolecular structure of materials. That means the interaction between the matrix components. In order to determine the rheological properties in this work, we will focus the attention mainly in the values obtained of the elastic G', viscous moduli G'', and complex viscosity. Materials with a solid-like behavior have high elastic moduli G' and low viscous moduli G'', while liquid substances have the opposite tendency, low elastic moduli and high viscous moduli, for example in the case of oil. Furthermore, the differences between both moduli will give an idea of the interactions inside the materials. The experimental procedure followed is shown in the slide. The ionic liquid 1-ethyl-3-methylimidazolium dimethyl phosphate is employed to dissolve 1% of eucalyptus or olive bleached kraft pulp at 100 degrees. Once the solution was finished, mixtures were poured into a steel plate at room temperature and they were at this temperature until gelation. The gelation time was set to 4 days after confirming through rheology that ionogels are formed and stable. Hydrogels were formulated directly from ionogels through the shifting of the ionic liquid by distilled water. Ionogels were immersed in incremental amounts of distilled water until conductivity remained constant. Formulated ionogels and hydrogels were characterized in terms of rheology and chemical structure, as well as morphology. Concretely, the rheology was based on dynamic frequency sweep tests that were conducted in both ionogels and hydrogels. All the tests were run within the linear viscoelastic region. In the case of morphology, we use scanning electron microscopy to determine the morphology of the subsequent hydrogels. The formulated ionogels present a solid-like behavior, as the elastic moduli G' is always higher than the loss moduli G''. Therefore, the formulated ionogels exhibited a dominant elastic behavior. In the plateau region, that is the region where we have studied our gels, all ionogels present a pseudoplastic-like behavior, as the complex viscosity decreased with the frequency was increased. Furthermore, the elastic modulus, viscous modulus, and complex viscosity are higher in eucalyptus than in olive ionogels. This is attributed to the presence of other compounds apart from cellulose that remain in the ionogel and do not contribute to increase the rheological properties as do not interact with the ionic liquid that is forming the matrix of our ionogel. These other compounds are hypothesized to be the lignin and the hemicellulose that are present in more percentage in olive pulps than in eucalyptus pulps. Other properties were also tested in ionogels. Concretely, it was checked that ionogels can be twisted and they are flexible as well as thermoreversibles. Thermoreversibility means that when you heat your ionogels, they recover their liquid state, and once they are poured again at room temperature into a steel plate, they come back to the gel-like state. Washing the ionogel with increasing amounts of water, the ionogel can be easily converted into hydrogel. The conductivity of the replaced water was monitored in order to control the ionic liquid that was being removed. After the fourth water replacement, conductivity remained constant at around 2 microsiemens per centimeter. This means that we are able to replace 1 gram of ionic liquid using 5 ml of water and consecutive washings. The consecutive washing is essential. That means that we cannot add directly the 5 ml of water to obtain an hydrogel free of ionic liquid. The shear rheological spectra in the linear viscoelastic region of both formulated materials are exposed in the slide. As occurred with ionogels, the storage model G' is approximately a decade higher than G'', indicating the gel-like properties of hydrogels in the studied range. The comparison between olive and eucalyptus hydrogels showed that G' and G'' values are slightly lower than in the case of ionogels. Furthermore, these values among both gels are pretty similar. That is something that differs from the previous ionogels, where we clearly saw that G' and G'' values in eucalyptus ionogels are higher than in olive ionogels. We hypothesize that the higher sealant content dissolved in the ionic liquid have increased the hydrogen bonding position available to be replaced by water during hydrogel formation in olive hydrogels. From the other side, longer fibers that are present in the eucalyptus pulp did not lead to free H-bond positions. Thus, both cellulose but especially hemicellulose content are pointed out essential to formulate hydrogels with high elastic and loss modulus. Furthermore, the higher content of lignin, hashish, and stactis present in olive pulps does not seem to worsen the rheological properties of formulated hydrogels. Finally, hydrogels were formulated by two different methods. Firstly, we used liquid nitrogen that was employed to freeze hydrogels, and they were subsequently dried using a freeze dryer. The pore size distribution showed higher pore sizes in olive than in eucalyptus hydrogels, with pore of even micrometers, that is pretty big. However, if we use supercritical CO2 to formulate the aerogel, pore sizes are much smaller, and we can reach mesoporous structures. Furthermore, we observed that the surfaces were much more homogeneous using supercritical CO2 than using freeze drying. These aerogels were structurally characterized in terms of Fourier transform infrared spectroscopy. FTIR spectra showed little differences between pulps and aerogels. First of all, the presence of H-bonds is evinced in the band that appears in the range from 3500 to 3200 cm-1. In both olive and eucalyptus aerogels, crystallinity decreases as a consequence of the dissolution process, which is observed in the decrease of these two bands that are principally 1317 and 1335 cm-1. The presence of lignin in formulated aerogels has also been reduced, which has been confirmed in the decrease of the band at 1424 cm-1. This justifies that during the ion shifting process to form the hydrogel, lignin remains in the ionic liquid and do not form part of the hydrogel. Finally, hemicellulose form effectively part of the aerogel, which is observed through the presence of the band at 1734 centimeters minus 1. With all this, we can observe the hypothesized structures that are shown in the slide. In the case of the ionogel, the matrix is formed by the ionic liquid and are also present the water that is trapped into the matrix, as well as cellulose, sealant, and lignin. In the case of the hydrogel, lignin has been removed as well as the ionic liquid, and the hydrogel is mainly formed by hemicellulose, cellulose, and water. In conclusion, ionogels and hydrogels have been effectively formulated using olive and eucalyptus bleached craft pulps. Formulated ionogels and hydrogels own a solid-like behavior and they are both pseudoplastic. Lignin content can affect the rheological properties of the formulated ionogels. However, lignin has been shifted with the ionic liquid during hydrogel formulation. Hemicellulose that is present in the pulp also contribute to hydrogel formation and also ionogel formation. We are able to obtain mesoporous aerogels using supercritical CO2. Furthermore, the ionogels that have been formulated are flexible and thermoreversible. Thank you very much everybody for your attention, and now if you have any question you want to ask, please feel free, and you can also reach me through my email direction that is shown in the slide. I also would like to thank my research group from the Complutense University of Madrid, as well as Ministerio de Ciencia e Innovación and Community of Madrid for supporting this research. Thank you very much.
Hello everyone. First of all, I hope you are all in good health. My name is Patrícia Henriques. I'm a PhD student at Instituto Superior Técnico in Lisbon, and in this presentation I'm going to talk a little bit about my work regarding the production of prebiotics using bleached craft pulp from Eucalyptus globulus. As you know, the world has been surprised with a terrible pandemic. We've all been struggling with the coronavirus for the last year, and by now we all know the most important measures to minimize the risk of contamination, like staying home as much as possible and reducing social contact, wearing a mask, and washing and disinfecting our hands regularly. Now the vaccine is finally here, which gives us some hope, but vaccinating the entire world population will still take a lot of time. So in the meantime, there is something very simple that most people forget that can not only help us against COVID infection, but also against so many other diseases, which is to improve our own immune system. And to do so, there are some simple things that all of us can do, like having a healthy and balanced diet, getting quality sleep, exercising, and trying to reduce stress. But if these things aren't enough, we can always take supplements to reinforce our immune system. A good example of those supplements are prebiotics and probiotics. And starting with probiotics, these are beneficial bacteria that are naturally present in our gut and can also be found in certain foods, like for example yogurts. They provide a lot of health benefits, including that positive impact on the immune function. However, a good performance of these bacteria relies on their nutrition, and that's why we also need prebiotics, which are food ingredients, mostly fibers, that humans cannot digest, but they are an excellent food for the probiotics, promoting the growth of that beneficial bacteria. This means that with the help of both these supplements, we can have a healthy digestive system that contributes to a strong immune function, which is extremely important right now. One example of prebiotics are xyloligosaccharides, which have great prebiotic potential and are now certified as safe products. They stand out for being market competitive due to the low daily dose recommended to achieve the desired prebiotic effects. These type of prebiotics, as the name indicates, are xylem-derived oligomers, and a great source of this semicellulose is bleached kraft pulp from Eucalyptus globulus that can have more than 20% of xylem. Once chosen the starting material, the xyloligosaccharides can then be produced by many different ways, and one of them is acid hydrolysis, which is quite a simple process with fast kinetics and low catalyst cost, and it's usually performed directly on solid xylem. However, it has the disadvantage of requiring high temperatures that can contribute to the production of unwanted byproducts, and the most common are xylose, furfural, and hydroxymethyl furfural. So, to produce these prebiotics from bleached kraft pulp, first the xylem had to be isolated, and for that it was extracted from the pulp with sodium hydroxide and then filtrated, generating an alkaline filtrate. Then, as this reaction is typically performed on solid xylem, a whole procedure to precipitate and purify the xylem was performed prior to the acid hydrolysis, and this here corresponds to route 1. However, in this work, we also studied a more unconventional approach, which was using the alkaline filtrate directly to the acid hydrolysis, and this, of course, will be our route 2. But as each alkaline extraction at the beginning of the process can result in different amounts of xylem, the results of the acid hydrolysis were normalized. And for that, we considered the yields of the sum of the different polymeric degrees from xylobiose to xylohexose per the initial xylem. And this initial xylem will correspond to the pure solid xylem for route 1 or to the xylem present in the alkaline filtrate for route 2. Besides the two different substrates for the hydrolysis, the solid xylem or the alkaline filtrate, other experimental parameters were also studied, like the type of acid, the temperature, the pH of the reaction medium, and, of course, the time of the reaction. After studying them piece by piece, we can then puzzle them together to give us the operating conditions that result in the best yield of xyloligosaccharides. So, starting with the type of substrate and acids, two different strong acids were studied, the nitric acid and the sulfuric acid. And for comparison purposes, we started by fixing a typical high temperature and a low pH value of 1. If we look first at the results using the solid xylem, we can see that there is a similar behavior of the yield through time for both acids, with a slightly higher value when using the sulfuric acid. With this, we reach a yield of 10% in 1 hour, while when using the nitric acid, we reach for the same time near 7%. Now, comparing with the use of the alkaline filtrate, it's clear that the kinetics is completely different from the solid xylem, resulting in higher yields. But even between acids, the behavior is very different, with higher values and faster kinetics when using the nitric acid. With this, we can reach almost 30% in 1.5 hours, while when using the sulfuric acid, we only get near 12% after 3 hours. So there is no doubt that the best results are for the alkaline filtrate together with the nitric acid, meaning that we will move on with this combination. Now that the substrate and the type of acid are chosen, it's time to study the effect of the temperature. And as I said, the acid hydrolysis usually requires high temperatures. So to confirm that, we compare the previous 100 degrees with slightly lower temperatures, as it is here also for 95 and 85 degrees. And from these results, we can directly confirm the need of high temperatures, as the maximum yield remains for 100 degrees. Just a very small change of 5 degrees can make a huge difference, resulting in much slower kinetics and also in lower yields, as we have the example here for 95 degrees, where the maximum value is 21%, reached only after 4 hours. We didn't consider values above 100 degrees because higher temperatures are known to produce high amounts of unwanted byproducts, and also as it would require pressurized equipment, which is also more expensive, meaning that we will continue with 100 degrees. The next step was the study of the reaction pH, as the acid concentration is also a very important parameter in this type of reaction. Here we have 3 different pH values, and at a first sight we can see that decreasing the pH results in faster kinetics. However, if we look at the simultaneous xylose formation through time, that I remember is an unwanted byproduct, the lower pH values also come with faster and higher production of xylose, which is something we really need to avoid. However, besides xylose, no other secondary byproducts were detected, so that's a really good thing. Looking back to the yield of xyloligosaccharides, we can see that the maximum yields for the lower pH values are very similar. We have 30% for pH 0.5 and 28% for pH 1. However, there is 1 hour gap between them, with of course the fastest kinetics being for the lower pH value, reaching that maximum yield of 30% within only 30 minutes. As for the highest pH that was studied, of 1.5, a maximum yield was not found even after a 5-hour reaction, meaning that we really need to focus on the lower pH values. If we now look at what we have in our mixture in terms of the distribution of polymeric degrees at the specific time for which the maximum yields were achieved, again, it's very similar for pH 0.5 and 1. In terms of xylobios and xylotrios, which are the smaller oligomers and also the most important, together they account for more than 40% of the total mixture in both cases, while for the bigger oligomers, from xylotetraos to xylohexose, they only differ in 1 or 2% between pH 0.5 and 1. However, we still have a very high amount of xylose in our mixture, being greater than 40% in both cases, and this here represents a problem because this byproduct is undesirable in food and pharmaceutical application, meaning that this solution is still not ready yet, and a further purification is mandatory. So, considering these very identical results between pH 0.5 and 1, we don't see any advantage in prolonging the reaction to 1.5 hours with pH 1, meaning that we can now choose pH 0.5 once we can reach the maximum yield of 30% within only 30 minutes. And now we finally have our puzzle complete. To summarize, in this work we found out that leachcraft pulp from Eucalyptus globulus is a great source for xyloligosaccharide production, a very important prebiotic. And the new and unconventional approach of using the alkaline filtrate directly to the acid hydrolysis not only is a simpler and more economic process, but also allowed us to obtain the best yields, meaning that with the chosen conditions, we can get more than 30% of xyloligosaccharides per initial xylem, and from this, more than 40% correspond to xylobios and xylotrios, which are the oligomers with the strongest prebiotic effects. Also, besides xylose, no other secondary byproduct was formed, which is a really good thing for this kind of reaction. However, we still have a very huge amount of xylose in our mixture, which means that our solution still has to be purified. Overall, with this new approach and chosen conditions, we can get more than 4 grams of prebiotics per kilogram of leachcraft pulp from Eucalyptus globulus, meaning that we can use this pulp to power up our protection against COVID infection. And that's it. Thank you so much for your attention. Now feel free if you want to ask any kind of questions.
Good afternoon for all the participants and for the speakers. Good afternoon, Dmitry. Good afternoon, Victoria. Good afternoon, Patrícia. Congratulations for your excellent presentations. There are some questions here. I think that your subjects were so very interesting that lot of people was asking questions. Let's start. This is for you, Dmitry. One question is how ash content affects dissolving pulp production, particularly straws such as a sugarcane bagasse?
Well, normally inorganic impurities are non-welcome to the dissolving pulp, but all will be depend how many ash we have and what kind of ash we have in the pulp. If it's alkali soluble and they dissolve during the reaction, it's one thing. But if it's insoluble ash, it can be really worst. If we're speaking such raw material from non-woody plants like wheat straw, for example, it's essentially silica and so on. This can be really dangerous because in this case we can have the cloring of the spinnerets and all related the problem in the production. But one again, it depends how many we have ash. If we have 0.1, 0.2%, I believe it's no problem. But if you have more than 1, 2, 3, or 5%, of course, it will be a problem.
Thank you. I have one question for Patrícia now. How do you characterize the xylem for saying there is no byproduct?
I analyzed the. I think so. I'm saying the question.
Okay.
I characterized the final product by HPLC, and I was just searching for xylooligosaccharide, xylose, furfural, or hydroxymethyl furfural that are the most common products for this kind of reaction. And we didn't detect any furfural in our analysis, so that's why I say there is no byproducts besides the xylose.
Okay, thank you. Now it's for Victoria. Why fibers from ion cell have so higher tenacity compared with the viscose fibers? Sorry, it's for Dmitry.
Sorry?
For Dmitry. Why fibers from ion cell have so higher tenacity compared with viscose fibers?
Yeah. It's very simple because there are no degradation of cellulose in the case of ion cell pulp. We should not forget that major processes steps in the conventional viscose production, we degrade the cellulosic chains, starting from the beginning with the mercerization till practically the end, the ripening. That's why the molecular weight decreased drastically in this case. And if you can see from the results that I present for the fibers from pilot scale experience, we can see that degree of crystallinity in this case much lower, and the crystallite weight also. So in this case, we have always lower strength properties. Lyocell actually is intermediate between ion cell F and the conventional viscose fibers. So my response is just very simple, much less degradation of cellulose in that process.
Okay, thank you. Maybe I will ask one question to Victoria. And one question is, what are the final applications of hydrogels? This was my question also.
We were thinking about using them in medical application, considering that the ionic liquid has been previously removed. Also, it could be useful for tissue engineering because depending on the percentage of cellulose that has been introduced in the process, we are able to phosphorylate the cellulose, and that could be useful for developing some tissue engineering materials on scaffolds. We were also considering to use them as absorbents, but maybe the added value of this application is lower than the previous one.
Okay, thank you. For Patrícia, Again, are there any inorganic impurities that were also detected in the final extracted product?
Yes, we also have, as we did an alkaline extraction and then an acid hydrolysis, we still have a lot of salts in our products. That's why it's not the final product yet. We still have to purify it, and there's a lot of things that we still need to remove.
Okay, again, one more question to you. Did you do any economic evaluation of your approach compared to existing one?
We are working on it, but as we still need to do the purify process, we can only close it when we have all the process chosen. But comparing to the other approaches that we usually see on the literature that use the solid xylene, we already reduce the process by attacking the filtrate directly, not precipitating the xylene, all that procedure that is needed to do that. So maybe it's more economic than the other approach.
Okay, thank you. And for Victoria again, how does lignin impact the hydrogels?
Actually, the lignin is dissolved in the ionogels, but when we add water for shifting the ionic liquid, the lignin is removed together with the ionic liquid. So we haven't seen high quantities of lignin in the hydrogels. That's why the mechanical properties of the hydrogels formulated with eucalyptus pulp and with olive pulps are pretty similar in terms of elastic and viscous modeling.
Okay, thanks, Victoria. For Dmitry again, how far is the ion cell process from large fermentation?
Yeah, really, it's one of the most close processes to the industrial implementation. Now it reached a pilot scale production, but as I know from the 2025, the first demonstration plant should be built. So this is quite optimistic because this process will theoretically replace the lyocell process.
Mm-hmm. And for Victoria, taking into account the differences in ash content, has been studied the influence of the ash content on the final properties? And another question, has the influence of ash content on final applications been considered?
Yeah, the thing is that if we use, for example, as final product the ionogel, the ash content will reduce the mechanical properties. But again, if we go to the hydrogel or the aerogel, we haven't taken into account the influence of the ash content in the properties. We haven't seen the presence of the ashes in the FTIR spectra, but we haven't gone further in that study.
Okay, there are no more questions from the participants, but maybe I can take some. I'm not a mechanic, I'm a chemical engineer, neither a chemistry, so I'm a little bit in trouble to understand all of your presentations. So I'm trying to concentrate more in the applications and the way your findings can be valuable, can be applied in the real world. I think that one of my questions was about hydrogels, but you have already answered. One thing when talking about xylans and these prebiotics and probiotics, you were talking about not non-wanted subproducts coming from this reaction. In the last session, I was assisting a presentation saying that some of these products, not wanted products from your point of view, are in fact good products for other utilizations. Can you comment that?
Yes, these products are not wanted for this application exactly. The goal is the xyloligosaccharides, not the xylose or the furfural. But the products that I call unwanted can be, I don't know, extracted and used for other purposes. We can combine two different goals, maybe.
Okay, I found it very very interesting, because I think that in fact you were talking a very important biorefinery model with different products. For some reactions or some purposes, some are not wanted, say, but for the other purposes they are wanted. So it's very
Maybe we can combine all together.
Combine everything. That's right. Um, when you are talking about the present pulp facilities, pulp mills, pulp processes, craft pulp process, how easy or how difficult it will be implementing this kind of process in the present mills? Do you have an idea?
I don't think it would be very difficult, because this process is, it's not very complicated. The first part is, it's done, the alkaline extraction. And then the production, it's simple acid hydrolysis that has been done for other purposes. It's an industrial application.
Okay. Dmitry, there is another question coming now, and the question is: have you tried also non-wood pulps to obtain viscose?
No, my purpose was just focused on the eucalyptus pulp. Well, I know that some of non-woody plants are already used for the viscose production, essentially bamboo, actually. But more than this, I heard a lot of, maybe dozens of different dissolving pulp, but they cannot compete with the conventional ones.
Maybe I can complete asking one question from my side. Is that, in fact, you are talking about the rayon fibers, as far as I understand, and as far as I know, I don't know too much about that, but all of these fibers are applied in the textile industry, for example, isn't it?
Most of them, yeah, practically, maybe 95 or even more %, yeah, true.
So what is the difference from the point of view of the application from ion cell and viscose?
The problem of conventional viscose fibers, actually, there are three. First of all, it's relatively low yield of viscose fibers, rayon fibers from the pulp. This is because of the method is not perfect. Environmental problems that we have is this viscose methods. And the third one, the low quality of the fibers. As you can see, the tenacity of the viscose fibers may be 2 or 3 times lower than the cotton. In this context, lyocell approaching the cotton, but IOCN is practically the same as the cotton. So from point of view of the quality of the fibers, ion cell arrive to the top of the rayon fibers now. Yeah, practically this is the most, I think, prospective method to do this. But not only this, because you know this method can do fiber engineering. In this case, if you want to produce fibers with some special properties, for example, hydrophobic or inopposite hydrophilic, or for example, antimicrobial or conductive fibers, we can do this. The conventional dissolving viscose method not allowed to do this. So from point of view of the perspective of fiber engineering, I think this is very interesting.
Okay. So
Actually,
there was one. Sorry. Please go ahead.
we did several work on this, and some of the work will be published soon.
Okay, there was one. I was saying that there was one question arriving, asking for the which horse should you bet on? Ion cell, lyocell, other in the textile industry. That's that's one question related to the previous one.
I think nowadays our technical facilities allows very well to manage with the conventional viscose process without any problem. 95% of the fibers are produced. But from point of view of the environmental concerns and the quality of the fibers, I think the future is for the or ion cell. But let me tell, when I was young and when I finished my school, people tell the same in the 80s. You know, when I finished my master course, people said the same. Now I must almost finish my scientific career and people tell the same. So let's say it's not very quick things in the techniques to do this. The major problems, of course, are the problems of the regeneration of the ionic liquids, also the prices, and well, some side effects on the environmental that we can have. So it's not so easy, but I believe that this will be a future.
Okay, thank you, Dmitry. Our time is finishing, but I'm still may ask this question to Dmitry also. Coming here is have you do you have any idea about how eucalyptus pulp compare with other hardwood and softwood pulps for textile production?
Well, actually, the eucalypt pulp I can compare perfectly with the birch. It's comparable with the birch, no problem. And in some aspects, even better than from softwood. In some aspects, yeah.
Okay, thank you. More 2 questions more. I don't know if I have time, but let's try. Patrícia, I will make this question 2 questions at the same time. So, since the washing step was omitted in second route, direct alkaline filtrate acid hydrolysis, how did you purify the XOX?
So as I said, we didn't purify the final solution yet. Okay. That's why it wasn't more detailed.
Something that you have to work on.
It's the next step.
Right. Okay. Somebody is asking if you can share some purification methods you are willing to use to purify the xylem, let's say for removal of the inorganic parts.
I don't know if I'm understanding correctly. I don't know if it's to purify the xylem or the xyloligosaccharides. But if it is the xyloligosaccharides,
the question is purify Okay.
I don't need to purify the xylem. I need to purify the xyloligosaccharides. Maybe that was it. And we are thinking about using nanofiltration to try to remove the xylose and some salt, and maybe ionic. The name is failing me in English.
No.
Permuta ionica. I don't remember. I'm sorry.
Ionic change.
Yeah, ionic change. Yeah.
Okay.
I'm sorry.
No problem. Okay. So I think that our time was running up. Again, I'm I was appreciating very much your presentations and the subjects and the themes and this these good ideas for transforming our pulp industry in new products and something that is a little bit so parallel to the pulp and paper, something that is important for the next future, for the next generation, for this bioeconomy, green life, all of these things. And I hope that you have good things in the future, and all the best for you.
Thank
Bye
you.
bye.
For you too.
Thank you.
Thank you.